Hello everyone. We are already a quarter of the way through this class. So this might be a good time to take stock of the situation and see where we are and reorient ourselves. So the first thing I'd like to do is say a little bit about the organizing principles of this course, just to make sure that we're on the same page. So you may have noticed that this class takes a certain approach to math formalism, which I'll call the Kanban approach. I don't know if you, well, maybe you weren't even, some of you were not even born then, but back in about 1990, there was a lot of talk about how the Japanese were going to take over every aspect of, they were taking over the semiconductor industry, and they just did everything well. And one thing that people talked about was that they used this Kanban approach to manufacturing, which was translated as just in time. So with small inventories, and they were extremely efficient about it. Okay, so what do I mean by a Kanban approach to math formalism? So what I mean is that, when in this class, I've tried to keep the mathematical formalism down to the minimum. So for example, when we talked about 2 qubits, I said, well, if you have the first qubit in this state, alpha 0, 0 plus alpha 1, 1, and the second qubit in beta 0, 0 plus beta 1, 1, then the state of the 2 qubit system together is alpha 0, beta 0, 0, 0 plus alpha 0, beta 1, 0, 1 plus so on. Well, if you want to do this formally, what you're doing here is computing the tensor product of these 2 qubit states. But rather than load you with all this mathematical formalism, what I want to do is put off this formalism as far as possible. The same is the case with measurements, where later we'll describe quantum measurements in terms of the measurement operator, and the measurement outcomes in terms of eigenvalues and eigenvectors of this operator. But once again, it's actually useful to talk about as much of this as possible without introducing all the mathematical notation. And that's what we're going to do in this class. Now, as we go along, as you get comfortable with these concepts, okay, we will actually talk about this proper mathematical formalism with which to discuss all these concepts. Okay, and so I hope that this is actually going to be better for many of you. It's a friendlier way of introducing the subject. And for those of you who already know the formalism or prefer to see it, well, you'll see it as we go along. Now, one of the reasons that I'm trying to introduce the subject in this way is that by keeping it light on formalism, it also highlights the counterintuitive aspects, the intuitive aspects of the subject. And once you look at things intuitively, you actually realize how counterintuitive quantum mechanics is. I think this is extremely important when you're doing quantum computing, because quantum computing actually, as a subject, it exploits some of the most counterintuitive aspects of quantum mechanics. And so if you're going to understand quantum computing at a deep level, you've got to grapple with these aspects of quantum mechanics, and you've got to understand them at an intuitive level. And so it's only by confronting your intuition with how strange quantum mechanics is, how strange its behavior is, that you can start forming this new level of intuition. Okay, so I hope that this, maybe some of you had already figured this out implicitly, but I hope this helps you understand how this course is being treated and organized. Okay, so the second thing about taking stock is, well, at the beginning of the course we conducted a survey to try to understand your background, and so this is probably a good time to actually conduct another survey to get a sense of your reaction to the lectures, the homework, how easy, how difficult you find it, whether you actually attempt the optional assignments and would you like to see more of those. How do you feel about your linear algebra preparation for this course? Would you like to see a review of the material? And if so, which topics would you like to see reviewed? And also, would you like to see some discussion of current research topics related to the lecture, what's being done in the lectures? So, for example, in the last lecture, I talked about the Bell experiment, and I said, actually, this Bell experiment is, it's the subject of current research in cryptography, in what's called device-independent cryptography, and in random number generation. So there are several, it is actually an active subject of research. And so maybe I'll give you a little bit of a hint, a little bit of a flavor of this current research. And then maybe in this survey, you can comment about whether you'd like to see more such vignettes or whether you'd prefer to see just the basic lecture topics. Okay, so let's let me just remind you what the Bell experiment setup is. Our apparatus was divided into two spatially separated parts, which we think of as two boxes. Each of those got a random bit as input, X and Y. Each of those output a bit, A and B. And what we wanted was that if X and Y were both 1, then we wanted the output bits to be different. In all other three cases, we wanted them to be the same. And what we said is that if the boxes are described by local hidden variable theory, so if there's some sort of classical description of what's going on in these boxes, then you can succeed in this task with no more than 75% probability. On the other hand, if the two boxes are allowed to share a Bell state, if they share entanglement, and if they measure these qubits in suitable bases, then they can succeed with probability as high as 0.85, cosine squared pi by 8. And in fact, in each of the four cases, they succeed with probability exactly 0.85 in that particular protocol. Okay, so now here's a problem. Here's a question that people have been trying to think about for a long time, which is, how do you construct a physical source of randomness? How do you construct a device which outputs truly random bits? Okay. So Intel last year announced a chip on which it digitally produces random bits for use in cryptography. But now you could ask the question, how do you know that the chip is working correctly? So in other words, you could ask, suppose you're given a black box which produces as output what it claims is a random string. How can you test it? If it outputs, let's say, 1,000 bits, how would you test that every one of the 2 to the 1,000 different 1,000-bit strings are equally likely? Or whether it's close to that? Well, classically it seems impossible to do this. But it turns out that you can use the Bell experiment to certify that you got real randomness. And the way this works is, if you run the Bell experiment, and if the experiment succeeds in its goal with 85% probability, or very close to 85% probability, then the only way it can happen is if the output bits A and B are random bits. Okay? So for example, you could choose to pick B and you could output it, and it would be guaranteed to be a random bit if you could certify that you succeeded with probability close to 85%. So now okay, so starting from this observation, there are schemes that actually show how to create a random number generator so that you can certify that the particular output that you've got must have been sampled from a distribution which is close to a uniform distribution on, let's say, 1,000 bit strings. Okay, so if you want to read more about how this comes about, here I've given you pointers, references to 2 different papers which have been posted on the archive. The archive is actually a good place for you to look for interesting papers on quantum computing. Okay, so that's an example of active research, very close to something we've already talked about in lecture.